Hello, good evening, everyone. Am I audible?
Yes, sir.
Okay,
Yes,
so
okay.
this is after 2 weeks we are meeting. We had a Diwali break. Today we'll start with BJT, Bipolar Junction Transistors. I'll go with some very basic theory of the transistor, of the bipolar junction transistors, and then we'll quickly jump into the questions which as far as gate exam is concerned, they are more or less related to the biasing of the transistor. So I'll be talking a bit about that, how are transistors biased. So there is what are the two junctions and how are they biased, and based on that we'll try to solve some problems, which as always we'll go through the problem, and then at the end I'll summarize the problem. We'll wait for 2 more minutes, and then we'll start the session. Okay, if you have any comments you can write down, or just speak up. Okay, thank you. We'll just wait for 2 minutes and then we'll start. There's a doubt that how do we convert digital to analog. How should I put this? You see that during op amps we saw that we can add two signals. So similarly, using an op amp, and there's something called an R to R ladder. So if we combine those two circuits, then what we can actually do is, um, we can convert a digital signal to an analog signal. Now just understand, let's take a very simple case. Let's say you want to convert a digital signal 111 into analog signal. So then you'll have to add. So we know that the first bit is 1 into,
Hello, sir.
yeah.
Your screen is not visible.
I am not presenting actually. Okay, then I guess we'll just start. Okay, I'll just start. Just wait. Is something visible now?
Yes, sir.
Okay, let me just first get this doubt cleared. Okay, which Priyanka asked. So what she asked is that how to convert a digital signal to an analog signal. Now there's something called an R to R ladder. So I'll not go into the depth, the details of it, but as far as I remember, it is an op amp. That much I recall, and an op amp, and then it's a negative feedback op amp. So this is the output node, and what we do is that we feed this using some, I think resistor is R here, and here we have a bunch of, let's say maybe 2R, 4R, 8R, and here is the bits, the first bit, the second bit, the third bit, and so on. So using this circuit now we can say that V out will be nothing but, so this will be what will it be? So if the signal goes through here, so it will be V in minus 0 by 2R equal to minus V out by R. Yeah, so I can simply write V out will be minus V in, so let's call this V in 1, the first bit, let's call it V in 2, so it will be V in 1 by 2 minus V in 2 by 4 minus V in 3 by 8. And I think there are some, this is not, but the form looks something like this. So it's type of an adder circuit. So using an adder circuit of an operational amplifier, what we can do is that we can convert digital to analog. More details I'll look up in the next class. Or Priyanka, you can just drop me an email and I'll reply during that. So but the basic idea is that to convert digital to analog circuit, you need an op amp in the negative feedback mode, and we provide a bunch of inputs on the left side. So you can see that the inputs are here, V in 1, V in 2, and V in 3 here on these sides, and then we can use, just due to the adder configuration, we can add them up. So that's how we convert digital to analog circuit. Is it somewhat clear, Priyanka?
Yes, sir, but there was in the analog to digital, you have used the formula that Vmax minus Vmin is equivalent to 2 to the power n minus 1. So in the reverse process, there is no formula.
No, I mean there are limits on that, but the thing is that you can see that there is a relatively simple thing. That's why the questions were with that. There can be formula. I'm not saying there cannot be, but I'm not aware of them. So that's the thing. So what I covered was that which was more or less related to some problems that were there in the exam. And since this was not directly in this directly did not come in the exam, hence I was not able to cover it. So that's what I am saying. But there can be questions. You're correct, since the syllabus says analog to digital converters and digital to analog converters. So digital to analog converters, in a way we covered it when we covered the adders. You remember in one question we did the adders, if you remember, we did one adder circuit for, sorry, we did one adder circuit in operational amplifiers. So digital to analog, a circuit can be used using an adder circuit. I do not have the formula right now. I'll try to bring it up into the next class. Okay, I'll just try to cover it if we have
Yes,
some.
sir.
Okay, yeah. So that's that. Now my screen is visible, I guess. Yes, is my screen visible?
Yes, sir.
Okay, so we'll go ahead and start with BJTs, and so I'll go. So this is the first video. I'm going to play it, and pause me if you are not able to hear it. Okay, I'm just going to play it now. Just 1 second. T2 paper reads as follows. For a bipolar junction transistor, which of the following statements are true? This was a GATE Physics 2022 problem. It's purely a theoretical problem, and this question covers almost all the aspects of the BJT that is there to learn as far as theory is concerned. This is a very, very simple question, a very thorough question. It covers all the concepts that are needed in BJTs. Okay, so let's listen to the question and the solution. Option A, doping concentration of emitter region is more than that in collector and base region. Option B, only electrons participate in current conduction. Option C, current gain beta depends on temperature. And option D, collector current is less than the emitter current. This is a multiple choice question with more than one correct answers, and we'll try to find out the correct answer or answers. The term bipolar junction transistor consists of three separate words. The word transistor means any device in which a third terminal controls the current flowing between other two terminals. So let's assume these are the two other terminals, X and Y. And if we were connect to, let's say, simply connect a tube between them, the water will flow, right? But that's not the case. So here we are deliberately introducing a barrier like this. So you note that the height of this barrier is barely above the water level on the left side. Now what will happen, since the water level is just barely above the barrier, so the small amount of water will flow. Now let's say somehow I am able to reduce this barrier. So what will happen, the water level remains the same, but more, since the barrier is lowered, more water can now flow. What happens if I raise the barrier? So if I raise the barrier will go above the water level, and thus no water can flow. Now note that although the water level is same in all the three cases and the elevation between left and right remains the same, it's the barrier which is controlling whether the water flows or not, and if water flows, how much water flows. This is the analogy that we can use in devices also. And this type of behavior is known as a transistor, where third terminal is controlling the flow between two other terminals. The second term in BJT is junction. What kind of junction we are talking about? And this is a very important term, transistor. We'll again in the next class also we'll cover the transistors. In that we cover a different type of transistor, which is field effect transistors, FETs. The most common form of FETs are MOSFETs, metal oxide semiconductor field effect transistor, MOSFETs. So there again the term transistor comes. As I explained here, the term transistor means a third terminal will control the current flowing between the two other terminals. So that's what we saw here. Just by lowering the barrier, raising the barrier, we are able to control the amount of water that, or the current that is flowing between the left and right terminal. We're talking about P semiconductor and N semiconductor junctions, and the word bipolar means two poles. Bipolar, two poles. What are the two poles? Electrons and holes. So the current in a BJT is due to electrons as well as holes. Both of them contribute to the current. Now, depending on how you join the PN junctions, you can have two flavors of BJTs. One is NPN BJT and the other is PNP BJT. We'll be focusing more on NPN BJT. So NPN BJT has electron as majority charge carrier. This means a majority of the current will be due to the flow of electrons, and very small amount of current will be due to the flow of holes. Right, and this is how the schematics of BJTs look like. So you have an emitter, you have a base, you have a collector. Emitter is N plus type, base is P type, collector is N type. Okay, now what do this N plus denote? This denotes that emitter is heavily doped. The doping in emitter is high. Why is it high? Because it has to provide a lot of electrons. The doping in base is low. Why is it low? Because so as to facilitate most of the electrons that are injected from emitter to the base, they go to the collector, they do not recombine in the base. If the doping of base is high, this means number of holes is high. Most of the electrons that are being sent by emitter will die in base itself and will get very less current at collector. We don't want that. Hence the base is low doped. Collector can be moderately doped. On the other hand, the width of base should be narrow, because we want very less time for electrons to spend here. The less time they spend, the less they will recombine. So base should be narrow. Collector should be wide so as to dissipate a good amount of heat. Heating has bad effects for any device, so we want collector to be wide so that more heat is dissipated more efficiently. And emitter can be moderately wide. Now, this is the NPN emitter base collector in equilibrium. Note that there are barriers here. You can see that there's a barrier to the electron flow. Electrons cannot flow easily. However, if we bias this NP junction, note that this is N, this is P. N is heavily doped, this is denoted by N++. So if we dope this as forward bias, this means N is connected to negative and P is connected to positive, this NP, correct? Then it is forward bias, then this barrier will be lowered and a huge amount of electrons can flow into the base. And if I bias this NP junction is reverse biased, N is to positive, P is to negative, this is reverse biased. So there will be a huge depletion region here, and the electrons, if they successfully pass through the base without recombining, a small amount will recombine, as you can see here. Small amount will recombine, right? Because there are many holes here. A small amount will recombine, but if we ignore them, you can see the heavy majority of electrons which are being diffused into the base can simply drift across the depletion region on the here, and they can reach the collector, and we'll get a collector current. So this is how the whole circuit diagram is. This is the working of an NPN BJT that we have seen here. A small amount will recombine. I re-emphasize that, and that's why we say that the current in a BJT is not just due to electrons, because some holes are being recombined, so it's being resupplied from the battery here, and hence the current flow is due to electrons and holes, and also some holes will diffuse from here to here. So the contribution of current from holes is there, but it is very small in a NPN BJT. And this is nothing but a KCL if you apply here. So IE is current, electrons are flowing here, current will be flowing out. Similarly, if holes are flowing here, so current will be flowing in. So IE is this, IB is this, and electrons are flowing here, so current will be opposite IC. If you apply KCL on this BJT, it will be current flowing out, which is IE, which is equal to current flowing in, which is IC plus IB. This is the expression, and this is what we call the current gain, beta. Beta is the current gain, which is nothing but IC upon IB. This is the mathematical expression. Similarly, we have another parameter called alpha, which is IC upon IE. So IC is the collector current, IE is the emitter current. This will always be less than 1, because some electrons will always get recombined here, right? But it's for a good BJT, it's very close to 1. So it may be 0.99 or 0.98, something like that. It's very close to 1. And beta is usually high. And this is all we're talking about in terms of the DC analysis. But that is not the complete picture. Beta is dependent on temperature, as you can see in this curve here. So we will not get into the in-depth that why is it so, but it's I can just comment that it is that as we increase the temperature, the beta, the DC gain, we saw the current gain, beta is nothing but IC upon IB. That increases as we increase the temperature. So we can see that beta is not constant with respect to temperature, and beta is not constant with respect to collector current either. Right? Now we get back to the question. Questions asked for a BJT, which of the following statements are true? We saw that doping concentration of emitter, so doping of emitter is more than collector and base. We saw that, which is required because it has to be the source of electrons in case of NPN BJT. So this option is correct. Only electrons participate in current conduction. This is not correct. We saw that electrons and holes also participate. Holes because there is some back diffusion from base to emitter and some recombination. So holes also participate. This option is not correct. Beta depends on temperature. We saw a curve in which beta is dependent on the temperature. This is correct. Collector current is less than emitter current. We saw that alpha equal to IC upon IE, which is will always less than 1, very close to 1, like maybe 0.9, but it will be less than 1 because some electrons will get recombined in the base. So this is also correct. So for this question, the correct options are A, C, and D. All right. Do you have any comments, any questions regarding the theory of BJT? Please ask. Any comments? All right. So I'll go ahead. So this was basically the theory part, that how what's the working of a BJT and things related to some constants like beta and alpha. Now we'll go ahead and we'll try to solve the problem, some of the problems relating to the BJTs. So there we'll bias. So you saw that in again share my screen. Sorry. I'll again share my screen. Just hold on a minute. Yeah, so you can see that here what we had done was that we saw this, that in this what we saw was that this was the NPN BJT that we saw, and we saw that this was forward bias and this was reverse biased. But there are 4 combinations. This is forward, this is reverse, forward, forward, reverse, reverse. So based on how we bias a transistor, what we can have 4 flavors. So these are the 4 flavors that we can have. So what are they? So they are, first is, so first is you can have base collector as reverse and base emitter as forward. This is the most common mode of operation. The base emitter is forward bias and base collector is reverse bias. This is what we call the active mode. So this region that you see, the almost the horizontal region, very slight slope, this is called the active region. And most of our the questions that we come from, we are used to, I mean our BJT operates in this region. The other region of interest is when both are forward bias. So your base collector as well as a base emitter is forward bias. That region is referred as saturation region. This is this region, you see, the linear region. So in this, BJT behaves like a resistor, because we know that I directly proportional to V is the relation of a resistor. So in this region, this behaves like a resistor. BJT behaves like a resistor in this region. The third is when base collector is forward bias and base emitter is reverse bias. This is called reverse active. We rarely use this. This is very rarely used. Very few applications here. And finally, when both are reverse bias, so the BJT does not even operate. Very few, like nanoamps of current flows through the BJT, and this is what is typically known as the cutoff region, which you see at the bottom of your screen here. So this is how the biasing of a BJT happens. So I repeat myself that most of our problems we operate in this region. So when base collector is reverse bias and base emitter is forward bias, and this is called the active region, and this is here we operate. You see the big region in the center, this is where we operate. Now sometimes the main aim of a BJT is to provide current to some load. Okay, so that's what we have here. So this is what we call a load line. Okay, so let's say that the resistance of a load is RL and the maximum power supply is VCC. So the maximum, so in the red, the maximum power that can be delivered is VCC, very simply, and the maximum current can be VCC over RL, and this is the line that we get. You simply join, because it's a resistor, you can simply join these 2 points and you will get a straight line, and this is called the load line. So wherever these two intersect, that is called the quiescent point or the bias point. We'll solve some problems and then we'll get to see this load line in a little bit more detail. So let's go ahead with that. All right. Right, now I'm going to solve the next problem. So just stay tuned. Let me play the video. Now looking at the question. Now looking at the question, we were given beta equal to 100, and this is the circuit, and we are required to find the collector current IC, where IC is the current flowing into the collector, IB is the current flowing into the base, and I is the current flowing out of this BJT. Secondly, since this is a DC analysis, we can assume the current flowing through the capacitors is 0, so no current flows through here or here. In a DC analysis, you can always assume that the capacitors are open circuited, right? Because the impedance of a capacitor is 1 upon j omega c, and for DC, omega is you can say to be what do you say? It's said to be 0. So the resistance comes out to be infinity impedance. Hence, it can be treated as open circuit and no current will flow through a capacitor in DC analysis. Remember, only in DC analysis. Finally, I can just name these nodes as the potential of these nodes as VC, VB, and VE, so that it's easier to understand which node we are talking about. Okay. And finally, what I am going to do to solve this problem, let's apply KVL along this line. Okay, along the green line, let's apply KVL in this circuit. Okay, and let's assume, for the sake of simplicity, the current here is I. Okay, so I'm going to write now KVL across the green line. So let's apply that. So we will write 12 minus 3k times I, or I times 3k. Then we'll go here. This will be minus. So now look at this leg. Since no current is flowing through here, if IB is flowing into the base, that IB has to flow through this resistor, correct? Because there's no current flowing here. So I can simply write this will be IB times 150k minus this potential drop, minus, let's for the time being write it VBE, right? VBE, some potential will drop here, and finally minus. So if IE is flowing through the emitter, all of this current will flow through this resistor. So I can write minus IE times 3k equal to 0. Now let's look at each of these terms carefully. 12 is a constant. I, we don't know what is I. IB is also unknown, VB is unknown, and IE is also unknown. So there are many unknowns. We'll try to figure them out. First, let's look at this term, VBE. Now, we assume that this BJT is in forward active mode, which that means that this PN junction is forward bias. And that means the potential drop, so this VBE we can simply assume it to be 0.7 volts. This is a very fair assumption. Why? Because we assume this BJT to be in forward active mode. So this variable is now known. Very good. So now the second thing is that now we can also write, let's keep IB as it is, and IE I can write, IE can be written as IB plus IC, correct? And IC can be written as beta times IB. So IE can be written as beta plus 1 times IB. Okay, so this term will be in terms of IB. Now IB is also here. Now we just need to find this term I. Now look carefully at this junction, at the node VC, which is being denoted here. Okay, so what I'm going to do, I'm going to write, let's say KCL at node VC. Let's see what's happening here. So what is the incoming current? Incoming current is I. What is the outgoing current? So it will be this. There's no current flowing through here, so I'll write it 0, plus there's current flowing through in this direction, downward direction. I'll write as plus IC, plus there's a current flowing through this direction. What is this current? Note that this is the current IB, nothing but IB, right? Because no current flows through here. So if IB is flowing through here, all of it has to come through this leg only. So I can write 0 plus IC plus IB, right? So again, so I is IB plus IC, and IC I can write it as beta IB plus IB. So I will also come out to be beta plus 1 IB. So now let's put, so I we have calculated is nothing but beta plus 1 IB. So now I'm going to solve this equation down here. Okay, so we have obtained that. I'm solving this here. So this is now 12 minus the value of I is beta plus 1 IB times 3K minus IB times 150K minus 0.7 minus IE is again beta plus 1 IB times 3K equal to 0. Now note that there is only one variable here, which is IB. Okay, so let's collect all the terms of IB, take them to the right hand side. So we'll get 12 minus 0.7 is equal to, we'll take IB common, so we'll get beta plus 1 times 3K plus 150K plus beta plus 1 times 3K. Straightforward. This is 11.3. This will be equal to IB, and this will be 150K plus beta plus 1 times 6K. Now I'll simply put the value of beta here. We know that. So this will be 150K plus beta is 100, right? It's given. So this will be 101 times 6. So that's 606K, right? And I'm going to solve it here now. So that will be 11.3. Now this is being followed here. So 11.3 equal to IB times, so 606 plus 150 is 756K. So this gives me IB as 11.3 upon 756K, right? So this we have calculated, and we know IC is nothing but beta IB. So this will come out to be 100 into 11.3 upon 756K, which is equal to, now let me get my calculator. So it will be 100 times 11.3 divided by 756K, which is nothing but, this is coming out to be 1.50. I'm rounding it off. It's actually 1.495. So I'm rounding it off, 1.50 milliamps. So we have calculated IC as 1.50 milliamps. We'll put this answer here. And that is all that was required for us to do. Just to summarize, this was a BJT given with some capacitors which we ignore in the DC analysis. The capacitor we ignore in the DC analysis, and we put down some voltages. And most important assumption was that the BJT is in forward active mode. This means VBE is 0.7 and so on. And we applied KVL, and we just obtained some expressions for IC, IB, and I, and we simply solved this question, and we got the answer. Okay, we have solved the problem using the analysis. So if you have any doubts, please ask. and otherwise we'll go ahead for the next question now. Any doubts, any comments? All right, I'll move ahead to the next question. Please stop me. I'll be repeating. This is a similar question, and again I'll be repeating many of the things so that it just gets ingrained in your minds. The problem statement from GATE Physics 2016 reads as follows. For the transistor shown in the figure, assume VBE equal to 0.7 volts and beta DC equal to 100. If Vin equal to 5 volts, V out in volts is. This is a numerical answer type question, and we are required to give our answer up to 1 decimal place. Before we start to solve any questions related to BJT, we ask ourselves a few things. First thing is, what is the nature? What type of BJT is it? Which BJT is it? NPN or PNP? If we note the symbol, the arrow is coming out of the emitter, and this means this is an NPN transistor. Second thing we ask is that which mode is this BJT operating in? Now note that if we are given VB equal to 0.7, this means that your base emitter is forward bias. But the question does not say anything about the collector bias junction. So we'll assume that collector base is reverse bias. This means this mode is what we refer to as the forward active mode, and all the expressions where beta equal to IC upon IB, alpha equal to IC upon IE, all those expressions are valid only when the BJT is working in forward active mode. So we'll assume that the BJT is in fact working in forward active mode. Now I've just read on the circuit diagram with beta equal to 100, and we have to find the V out with V in equal to 5 volts. And I've drawn the currents. The current IC is flowing into the collector and also through this resistor. Similarly, IB is flowing into the base and through this resistor of 200 kilo ohms, and IE is flowing out of the emitter and consequently through this resistor of 1 kilo ohms. Secondly, what I have done is that I have just given some node voltages. So this is VB, this is VE, and this is the collector, which is from where we are measuring the output voltage as V out. All these voltages are denoted in blue color. Now what I am going to do, I am going to apply KVL across the screen line. Now follow me carefully. We are going to apply the KVL across the screen line. Why I chose the screen line? Because I know what is the VBE drop here. So I can simply apply this here. This was given in the question, by the way, and in forward active we assume it to be 0.7 volts. So we'll just apply the KVL across the screen line and let's see what it comes to. So I'll write the KVL expression is V in minus IR, which in this case is IB times 200K minus VBE, note this drop we have reached here now, minus IE times 1K, which is equal to 0. This is the simple expression. So we know V in is 5, which was given, minus IB times 200K minus, I know VBE is 0.7 minus, and I also know I is nothing but beta plus 1 IB times 1K equal to 0. How does this come? We know that IE is IB plus IC if you apply KCL across the BJT, and this is IB, and IC we know is beta IB. So IE comes out to be beta plus 1 times IB. Simple expression, and I have just used this expression here. So let's keep IB terms on one side and the constants on the other. So we'll get IB times 200K plus beta plus 1 times 1K is equal to 5 minus 0.7 is 4.3. So I'll get IB into, so let's put beta equal to 100. So I'll get 200K plus 101k, which is equal to 4.3, and from this I'll get IB as 4.3 upon 301 kilo ohms, right? And we were required to find the V out. Now note that so we are required to find V out, right? So this is the second step. So V out is nothing but if we apply KVL simple here, so I can write, or we can apply Ohm's law across this 3 kilo ohms resistor. So I can write, sorry, just ignore this. So it will be 10 minus V out is equal to IC times 3K, simple. Ohm's law across this resistor, right? So now I'll write V out equal to 10 times 3K times IC, and I know IC is nothing but beta times IB, and beta is what, 100. So I'll just write the expression beta times IB, which is equal to 10 minus 3K times beta is 100. IB we calculated this value 4.3 upon 301K. So what's going to happen is I am just going to solve this expression here using my calculator. So the numerator is 300 times 4.3 divided by 301, which is nothing but 4.29. So it's 10 minus 4.29, and thus V out comes out to be 10 minus 4.29 is 5.71. So this comes out to be 5.71 volts. So we have calculated V out as 5.71 volts, right? Okay, so this is the V out, and this is what we are required to find out. So we can simply write V out as 5.71 volts. Okay, now we can also check one thing. So we calculated this value is 5.71 volts, right? We assume that this is reverse biased. So let's just check that. And we also calculated that this value. So IB we calculated, right? So IB was 4.3 upon 301K. So let's calculate this value. So that will be 4.3 divided by 301. So that will be around 14 microamps. So this is approximately 14 microamps. Okay. Thus, and this is 5 volts, right? So what will this node be? So this VB will be equal to 5 minus 14 microamps times 200K. So this will come out to be, I'm just calculating it for you. So this will come out to be, just a second. So this is coming out to be 2.14 volts. Okay, so this node is at 2.14 volts. Now we can clearly see that this is reverse bias. Note that this is the NP, this is NPN trans. So this is N and this is P. So N terminal is at a higher potential as compared to the P terminal. So this junction is clearly reverse bias. So, and we assume that, right, that collector bias should be reversed, and it is coming out to be reversed because collector is at 5.71 volts and base is as 2.14 volts. So this is clearly a reverse bias. So our assumption is correct, and we calculated using this assumption of forward active mode that the value of V out is 5.71 volts. And since one decimal place, so we can simply write it as 5.7. Note one decimal place. So 5.7 is the answer. Okay, so this was the second question related to the biasing of a transistor. So these are the typical problems that we see. Now I'll solve the next problem will be similar to this, but I'll add one more concept, and that is of the load line. This is a very simple concept. We'll simply just solve our BJT in the biasing that we assume the forward active mode, and we'll simply put a load line. There's nothing fancy about it, and we'll just see that in a minute. So let me just open the question first, and then we'll try to solve the problem. Okay, just hold on a minute. All right, so I hope you can see my screen. So this is a problem that we are given here. and it says that this is the circuit that we have been given. So this is a BJT. We can clearly see that this is an NPN BJT, and this is the first thing we need to identify. Second thing, we need to check whether this is in forward active mode or not. Forward active. Sorry, just excuse me for a minute. So I'm not able to write for some reason. I'll try to do it. So we'll check whether it's forward active mode or not. This BJT is forward active mode or not, and then we are required to find the output characteristic. So what is the IC? You see this Q point, this is nothing but we just need to find out the value of the Q point. But that is, what does the Q point mean? The collector current IC and VCE. That is the meaning of the Q point. So we'll just need to simply solve this circuit, and then we'll find the Q point. So I've just redrawn the circuit here, as you can see, and I'll try to solve this now. So what we'll do is that, again, I'll try to apply the KVL across the green line, and we need to find the Q point, which means the IC and V out we need to find out. IC is the current flowing through this branch and through the collector. IB is the current flowing into the base, and thus IB will also flow through this 100 kilo ohm resistor. IE will flow through out of the emitter of the BJT, and thus through this 100 ohms resistor as well. And now we'll simply apply the KVL across the green line, as I mentioned here. So I'll write 15 minus IB times 100k minus VBE. This is VBE, and we know that VBE must be equal to 0.7 because this is a forward active mode. And then finally minus IE times 100 equal to 0. Right, so I'll just simply put the constants on one side. So that will be 15 minus VBE is 0.7, we know that. So I'm writing this VBE minus is 0.7, and then I'll simply write this as IB times 100k, right? And then I'll write plus IE is nothing but beta plus 1 times IB, right? We saw that just now, and the value of resistor is simply 100, right? So this will come out to be 14.3, and on the right side we get, I'll take IB as common. So if I take IB as common, what will I get? I'll get 100k plus beta plus 1 is nothing but beta was 100, so this will come out to be 101 times 100, right? So 101 times 100, this will be 10.1k. So from this I'll get IB is equal to 14.3 divided by 110k. This is the value of IB. And note that for Q point we are required to find the value of IC. So I can simply say IC equal to beta times IB. This is nothing but 100 times IB. So that will be 100 times 14.3 divided by 110k, which will come out to be, if we solve this will come out to be 13 milliamperes. So this is simply 13 milliamperes, right? And finally we need to find the value of V out. Now we saw in the previous question also, V out is nothing but if we apply the Ohm's law across this resistor, the 900 ohm resistor. So I can simply write that V out is equal to, that's 15 minus IC times 900. So if we solve this, so this will be 15 minus IC is 13 milli times 900. So this will come out to be around 13 times 900, it will come out to be around 117. So this will come out to be around, we will calculate this, the 13 times 9 is 11.7, so that will come out to be around 3.2 volts, right? So this potential, this node that we are seeing here is at 3.2 volts. We just saw that. Now, and we can also calculate, just to check whether this is clearly in reverse bias or not, we can also calculate the values here. So we can simply just this is coming out to be 3.2 volts. So if we see, IE will also come out to be around 1.3 volts, and this will be 2 volts. So this is again, so this will come out to be 2 volts, and this is at, we calculated at 3.2 volts. So we can clearly see that this is an NP junction, and this is again reverse bias. N is at a higher potential as compared to the P junction. So again, so what we saw was that, so we saw that the current came out to be around 13 volts, 13 milliamps, sorry. So 13 milliamps was the current, but the, so, and the we were required to find VCE, sorry. So if we calculate VCE, so I also need to calculate VE here. So VE will be nothing but, how do we calculate VE? VE is nothing but, if we apply Ohm's law across this resistor, so that will be IE times 100. So IE times 100 will come out to be, IE is approximately equal to IC, so that will be 13 milliamps times 100. So that will be around 1.3 volts. Okay, so this is coming out to be 1.3 volts. And VCE, note that question required to find VCE. So VCE is 3.2 minus 1.3 is 1.9 volts. So the closest option that we have is A. So no, Q point is nothing but, it is defined as in this circuit. Q point is nothing but the value VCE that we saw here. And we first calculated simply using KVL, we calculated the collector current flowing through here, which came out to be 13 milliamps. So this option, only this option is correct. We also find the value of VCE, which came out to be approximately 2 volts. So this is the correct option. And I told you the relevance of this straight line, that if we draw a load, which in this case is this, so some value it will always fall along this line. The maximum value it can have is 15 volts. This is the value here, we saw that this is the 15 volts that we saw here, and the maximum drop that can happen across this region is 1k. So 15 upon 1k is 15 milliamps. This, how did this come out to be? This is coming out to be 15 volts. This is the maximum voltage that we can have, the maximum voltage here, divided by 900 plus 100, which is 1k. Hence this came out to be 15 milliamps. So now we come to the last question, and this in the very early classes, I think I don't remember, in the second or third session, somebody asked, how do you create a current source? I think that was in the very second class. How do you create a current source? So here what we have done is we have created a current source, as you can clearly see here. So here the current source is being created, you can see. So current source, how is it being created? So you can see that, just look at the right and on your left. Okay, so the current through BJT depends only on the VBE, the value of VBE, and some other values, but we'll assume that these two are identical transistors, Q1 and Q2. Then it only depends on VBE. So you see that for Q1, that their bases are at the same potential. You see this node and this node, they're at the same potential, and similarly this node and this node are both at the same potential, which is ground. So this means that I can say that VBE1, which is equal to VBE2. This implies IC1 is equal to IC2, and this is what is called as this is what is we call it as a current source, a simple current source, or a current mirror, because whatever current is flowing through here has to flow through here. So this is what it says, and again we'll assume both of them to be in forward active mode with gain equal to 100 and VB equal to 0.7 volts, and we are required to find the value of this term I naught here. So what I have written is I have just reproduced this circuit here, and what I'll assume is that a current, so let's just put some currents down. So let's assume this current would be, so if this this current, let's assume to be IE. Okay, so this current will also be IE because they're current mirrors, they have the same potential and everything. VB is the same for both. And let's assume this current is IB. Naturally this current will also be IB, the current flowing into this transistor. So if you apply KCL here, the current flowing here would be 2IB. Why 2IB? One IB will go here and the other IB will go, sorry, one IB you see will, 2IB is coming down, so one IB will go to the left and the other IB will go to the right. And I'll assume that the current here, this is again IC, right? And this, so the current here, so this IC will be nothing but I naught. Why? Because they're current mirrors. So the current flowing through this branch, through 5K, if we apply KCL here, will be nothing but I naught plus 2IB. Very simple. So the current flowing through here will be nothing but I naught plus 2IB. Remember how you calculated this? The current would be the same here, IE and IE, because they are the same, they are effectively this, the biasing is the same for both. IB will also be the same for both, so I apply KCL here, so this will be 2IB flowing through here, and the current here will be nothing but the same as this I naught. So this I naught and this I naught will be the same, so current here will be I naught plus 2IB. Now what I'll do is again the very famous thing that I do. I'll choose the green color, so I'll apply KVL across the green line. So when we apply the KVL across the green line, then we can simply write that's 30 minus IR, that is R is 5K, times what? I naught plus twice of IB, right? And then there is no current drop here, and then there will be a VBE drop here, so this will be minus VBE again, because we are in forward active mode, we'll assume that the drop is 0.7. This should be equal to 0. Very simple. So that this will come out to be 29.3 equal to 5K times, now I naught is nothing but IC here, remember that. So but let's just keep it to be I naught plus twice of IB. Now I can write that beta is equal to IC. So IC, the value of IC here is this upon IB. So IB will be nothing but I naught upon beta. So let's put this here. So this is 2IB, so twice of this will be I naught upon beta. So from this I can get I naught is equal to, that will be 29.3 divided by 5K times, this will come out to be 1.02, because the value of beta is 100, 2 upon 100 is 0.02, and if you add it with 1, so it will come out to be the value which I have written here. Let me just put these numbers into my calculator so as to get the final answer. So that's 29.3 divided by 5K divided by 1.02. So the answer that is coming out is 5.74 milliamps. So the current that is flowing through this arm, and as a result to this, the collector of Q1 is 5.74 milliamps, and this is what we were required to find here. So I can here simply place as 5.74 milliamps. So two decimal places is the required that we were required to find, which we find out as 5.74 milliamps. So yeah, so that's all that was there to do in this question. And in fact, we are done with the complete questions with as far as BJT is concerned. So if you have any comments, any questions, please feel free to ask. In the next class, obviously, I'll try to um, uh, are you able to see my screen now? Anyone?
No, sir.
No, sir.
So throughout the question, was my screen visible?
Yeah.
Okay, so it went out only now. That's good. I was afraid that you could not see the question. So this the current mirror question was just very is a very practical application of a BJT. This is very commonly used. So we keep on hearing that you ideal current source and so on. So how does an ideal current source actually implemented? So this implemented using a BJT. This is very famous practical. How should I say, the practical application of a BJT. So in today's class we saw some how to bias the transistors, and we basically bias the transistor in forward active mode. So you saw that we just simply use KVL expressions, and beta equal to just the value of beta and the fact that VB equal to 0.7. Just using these three things, we solved every question relating to the biasing of the transistors. Now please note that in today's class we only solved the DC analysis, right? Because all the voltages were DC. In the next class, we'll solve one question, which is the AC analysis of BJT, and also we'll try to finish up with all the remaining questions of field effect transistors, the MOSFETs, which I talked about in a brief, the other type of transistors that we have. So yeah, that's it from my side. If you people have any comments, any questions, please feel free to ask. In the next class, I'll try to clarify the Priyanka's doubt regarding what was it, digital to analog, if I remember correctly, right, Priyanka?
Yes, sir.
So in the next class, I'll bring a couple of slides regarding digital to analog circuits, and we'll go through that. It will not take much time. And the idea of these classes is to clear your doubts and you can clarify a concept. So we'll do that. So, any doubts? Any comments?
Sir, in the last circuit, how can we show that the resistor, that the current is independent of resistor?
Okay,
Can we show?
I'll just open it. Yeah, that's a good question. That how is it independent? Then only it remains a current source, right? That's what you are arguing. A current source is independent of the resistance.
Yes.
Yeah. So let me just open the. I hope my screen is visible. Yes.
Yes, sir.
Yeah. Okay. So you can see that what I told you. Sorry. Excuse me. Yeah. So what I told you is that since, see, now look at this transistor. So what will determine the current? So I can write that I naught, this current I naught will be nothing but IB2 plus, I can simply say IB2 times beta plus 1 times IB2, correct? This is what I can write. Okay? And what I do know is that IB2 is equal to IB1. IB2 is equal to IB1. How I am saying that is because these two transistors are exactly the same. See, the base is at the same potential for these two transistors as well as the emitter. So as long as the base and emitter are the same potential for these transistors, now these transistors are equivalent as far as the current flowing through them is concerned. They may be different in other aspects, but the current flowing through them is constant. Now whatever resistor you may apply here, whether you apply 10k or you apply 100k, it's independent. The current, this current I naught depends only on what is the voltages here, B, VBE, and that depends only on this circuit. It does not depend on the current here. The current of the value of I naught depends only on the value of VBE here. That's it. That's the only thing it depends upon, right? And this VBE is determined using this circuit on your left. It's not dependent on the right. Hence, we are fairly certain that whatever resistor you may apply, this the value of I naught will not change at all, because it depends only on the left circuit. You saw that the value of I naught is independent, is not dependent on any of the terms here. It's dependent only on the terms of this 5k of this VCC. You remember the KVL expression that I wrote that 30 minus 5 times some I naught expression minus 4 minus 0.7 equal to 0. So the value of I naught is dependent only on this value, the VCC, the power supply, and this resistor, the bias resistor. That's it. And that's how we are fairly certain this is a good current source, because it does not depend whatever resistor you may apply here. So that was the reason. Is it clear, Pratik?
Yes, sir.
Yeah. Okay.
Yes, sir, it is clear.
Okay, good. That's good. Okay. Any other doubts, any comments people have? Please feel free to ask. If not, we'll close this session. Next week will be our last session as far as this round is concerned. If there are any other follow-up sessions, please visit the Gate NPTEL page. The updates will be there. Maybe NPTEL will also send out emails regarding if any future sessions we might have. Most likely we'll have, but I'm not certain because that's from the administrative side. But just keep visiting the website if there is any chance. And anyways, you can always keep writing to me. You have my email. I'll again share my email with me. Email with you here. Yeah. And the videos of specific questions will, I think NPTEL would start uploading soon, very soon. So because in, I think 2 weeks or 3 weeks back, at least one of you asked that when will the videos be available of questions solutions. So they'll be uploaded. We are editing them right now. So hopefully they'll be up soon, much before the gate exam. So if you have any further doubts, just visit those videos for electronics from me, and there are many other people who are doing very fine work with regard to quantum mechanics, mathematical physics, and other subjects. Please feel free to do that. And yeah, leave comments if you like. Just send an email if you don't feel comfortable with the comments, and I'll try to get back to you. Okay. If no other doubts, then we'll wrap up for today. See you for the next week for AC analysis of BJT, the digital to analog conversion, and field effect transistors. So that's all from me today. Thank you. Good night.
Thank you, sir. Good night.
Good night. Bye bye.
Thank you, sir.
You're welcome.